Good morning. We are continuing with, excuse me, Unit 7, differential equations. Today we are looking at the logistic model. Sorry. Recall that population growth was dy dx equals ky. This is only approximate for short periods of time. And if you recall from yesterday's lesson, this is the one that will turn into y equals y sub 0 e to the kt, or p equals p sub 0 e to the kt, your PERT formula from pre-calculus. So that's what that one turns into. But that's only true for little bits of time. That's kind of the bottom of this curve here. We know that is exponential growth. But the truth is population can't continue to grow forever and ever and ever. Resources are limited, space is limited, food is limited, disease comes through, whatever it might be. In years past, students have told me that they've seen this in their biology class. So this is where math can model science. When we talk about it leveling off at the top, we use the logistic equation, the logistic model. And so that takes into account something called the carrying capacity. And the carrying capacity is the absolute limit, the absolute maximum population that we can have. So we have that exponential growth happening, but then at some point it has to level off. At some point it has to level off. So we've got a couple different situations that we could be starting out with. Oh, by the way, this is the logistic equation for the rate of change of the population. So it's that ky, which is true, and then times this 1 minus y over a piece. K is the growth constant, which is greater than 0 because it's getting bigger and bigger. A is the carrying capacity, or the limit. So if y sub 0, that initial amount, if y sub 0 is greater than a, we decrease towards a. So if you start out with y sub 0 up here, it will decrease until you reach a. So that population will start to die off until you reach a. If a is greater than y sub 0, or y sub 0 is less than a, if you start out down here, your population will increase until you hit that carrying capacity. And if y sub 0 is less than 0, so if your initial population is less than 0, which seems pretty abstract, it will tend towards negative infinity, or it does not exist. So it will continue down in that direction. But that's what your logistic equation looks like. So let me erase this off of here again. Two things to note. I guess one thing to note. The maximum growth rate, max rate, I'm seeing this on released AP questions, the maximum growth rate is at 50% of the carrying capacity. When you look at this picture, it's where the slope is the steepest. So say your carrying capacity, I don't know what it is, 100 whatevers, then the maximum growth rate happens when your population is at 50, whatever it might be. So max growth rate, 50% of the carrying capacity. So solving the differential equation. Once upon a time, I used to sit in class and do this. dy dt equals ky, 1 minus y over a. And it would take 20 minutes to do whatever. So I'm going to do kind of an abbreviated version here. You have dy, bring your y over. K, actually you have to bring back, see, I goofed already. Y, 1 minus y over a equals k times t. All right, so I've separated the variables, and yes, you can integrate this. The right-hand side would be kt squared over 2 plus c. The left-hand side, because we have this y times 1 minus y over a, you have two things being multiplied. This is actually partial fraction decomposition. Partial fraction decomposition. And you can go through all those steps and solve. I don't want to do that. In fact, I'm looking at my notes from last year. This is magic math. At some point, I used to teach this lesson before we did partial fraction decomposition, so we didn't get all the way there. But anyway, know that you can go through and you can look it up on how to solve that. But your final result is a over 1 minus c e to the negative kt. So let's back up a little bit. just like this differential equation goes to this, what do we call that? That general solution, I guess, that general solution where we have the y. This differential equation that's a little bit more complicated matches up with this general solution. So again, if you're interested, if you want all that math where it comes from, I'm sure there's a YouTube video out there for it. In fact, I can find a link if you want, but we're not that interested. Just know that this differential equation turns into that general solution. We'll call it good. All right. So we want to solve dy dt equals 0.3y times 4 minus y, where y sub 0 equals 1. So I was given this initial condition. And I zoomed out here for a second. Remember that we have dy dx in this form, and I just want to make sure I copy it correctly. Ky 1 minus y over a, and we know that this will turn into the form y equals a over 1 minus ce to the negative kt. Okay. Oops. Come on. Sorry, I'm trying to shrink this so it doesn't take up the entire space. There we go. All right. The problem with what I was given is it's not in this same form as what I had. So we need to change that. So I need ky 1 minus y over a. The problem is this 4. The 4 needs to be a 1. So mathematically, how do I make this 4 a 1? I'm going to factor out a 4. So dy dt is equal to 0.3y. Here comes the 4 I factored out. This is now 1 minus y over 4. It looks like this. Okay, so in the front, 0.3 times 4 is going to be 1.2y. 1 minus y over 4. Remember, factoring is just division, so I divided that inside by 4. Now, let's take note as to what's what. Your k is the value in front of the y. So k equals 1.2. And your a is what's underneath the y. So your a is equal to 4. Now, we take those pieces and put them into the solved general solution. So y is equal to 4 over 1 minus c e to the negative 1.2 t. So there's my general solution. But how do I come up with a specific solution? Well, that's where we use that initial condition. So 1 is equal to 4 over 1 minus c e to the negative 1.2 times 0. Negative 1.2 times 0 is 0, and e to the 0 would just be 1. So 1 equals 4 over 1 minus c. I'm going to cross multiply, or basically multiply the bottom by, or both sides by 1 minus c. So 1 minus c is equal to 4. Negative c is equal to 3, so c is equal to negative 3. So y is equal to 4 over 1 minus a negative 3, so plus 3 e to the negative 1.2 t. There you go. We solved that differential equation. So instead of us solving this from the beginning and separating the variables and using integration, partial fraction decomposition rather, you can just jump to this formula. You know that this form turns into this form. Okay. Example 2, we have, and I hate the way this is worded. I keep meaning to change this every year, and I never quite do. A 10,000 acre forest with a carrying capacity of 1,000 deer. K is equal to 0.4 per year. Find the deer population when P sub 0 equals 100. So basically find the deer population in terms of T with respect to time. So at any time. That's the piece that's missing there. So for letter A, we know that K is 0.4 inverse years. Excuse me. A, your carrying capacity is also given, which is 1,000 deer. So we don't need the differential equation in this one. We can use that final version, that solved piece. So y is equal to A, 1 minus c e to the negative kt. So 1,000 deer, 1 minus c e, k is 0.4, so negative 0.4 t. Okay, good. Now, when the initial population is 100, that word initial or that sub-zero is a sneaky way of saying time equals 0. So we can say 100 is equal to 1,000 over 1 minus c e to the negative 0.4 times 0. 100 equals 1,000 over 1 minus c. Now, how do we solve this? I'm going to cross multiply. I'm going to say that 1 minus c is equal to 1,000 over 100. 1 minus c is equal to, cross off the 2 zeros, we get 10. By the way, that's over 1. So negative c is equal to 9. So c is equal to negative 9. So when we put this all together, y is equal to 1,000 over 1 plus 9 e to the negative 0.4 t. So that's my deer population at any time t, and that's not really asked very well in the question. Letter B, when will the population be 500? The other thing I think of with these is I think of them as kind of, you know, the PERT formula version 2.0. So it's the same skill that you did in pre-calculus with these problems. You're just using a more complicated equation. So when will the population be 500? So same formula, but we're going to say 500 is equal to 1,000 over 1 plus 9 e to the negative 0.4 t. And we need to solve for t. So again, we're going to do that cross multiply switcheroo here. This is over 1. I guess I'll do this in 2 steps. We're on video and I don't want you to get lost. 500 equals 1,000. Divide both sides by 500. So we get 2. So 9e to the negative 0.4 t is equal to 1. E to the negative 0.4 t is equal to 1/9. How do we deal with that e? Well, we introduce natural log. Natural log of 1/9. Those cancel out. Negative 0.4 t is equal to natural log of 1/9. T is natural log of 1/9 divided by negative 0.4. Oops. And if I put that in my calculator, because that expression doesn't mean much to me, it's 5.493 years. Okay, there you go. That's our logistic equation. So it's the same process that we had yesterday with the differential equations and exponential growth. And it is just a fancier version of the PERT formula that you had in pre-calculus. So give these a try. I'm sure you're going to have questions on some of the wording, but make sure you reach out and ask.